We will now discuss the weak star topology. So V is a Banach space and V star is the dual space. So V star, you already have the norm topology. V star is a Banach space, we also have the weak topology. What is the weak topology? Smallest topology such that every element of V double star is continuous. So this would be the weak topology on V star. Now we are going to define the weak star topology. So definition: the weak star topology on V star, so this is always defined only on the dual space, is the smallest topology, smallest in the sense of smallest number of open sets, such that the functionals Jx, x belonging to V, are continuous. Recall, J is the canonical embedding from V into V double star. Jx acting on any f is nothing but f acting on x, which in the old notation is f of x. Of course, this is for every f in V star, for every x in V. Okay, so this is so V double star, all elements of V double star continuous, it's a weak topology, but we are only now asking for a smaller number of functionals, namely the functionals of the form Jx to be continuous, and therefore this gives you a smaller topology. So immediate remark: V reflexive means J is onto, then there is nothing new. Weak and weak star topologies coincide on V star. So this makes sense only in the non-reflexive case. So if V is finite dimensional, then it is reflexive, and we already know the weak and norm topologies are the same. So norm, weak star topologies coincide. Okay, so there is nothing absolutely new in those cases. Okay, so if you have weak star is the weak star topology, so this is contained in the weak topology, this is contained in the norm topology. This is norm topology, this is the weak topology, and this is the weak star topology. So this is the inclusion between them. And then, okay, so first immediate proposition: any self-respecting topological space better be host of. So proposition: weak star topology is host of. Okay, so proof. So what should you do? You should find two weak star open sets. If so, let f1 not equal to f2 in V star. So what does it mean? That means there exists a x in V such that f1x is not equal to f2x. This is what we mean when two linear functionals are not the same. So let us take u1 neighborhood of f1x, u2 neighborhood of f2x in R or C if you are dealing with complex spaces. Then u1 intersection u2 is empty because the real line or complex plane is itself housed off. So you take Jx inverse u1. This is the set of all f in V star such that f of x belongs to u1 and Jx inverse u2 is set of all f in V star such that fx is in u2 are both weak star open by definition because it's Jx inverse something and disjoint, and you have f1 belongs to this and f2 belongs to this. Okay, so you have weak star neighborhoods of this. So we can now also define how is a typical neighborhood. So typical neighborhood of f in V star in weak star topology. So U must be set of all f in V star such that, so just as we had the weak neighborhood was f minus f naught less than epsilon, so you have j of x minus so neighborhood of f naught. Okay, so set of all f such that, so mod f minus f naught xi less than epsilon where I in I, so for all I in I if you like, where I is a finite indexing set and xi is in V for all I in. So you take a finite number of points, so you take jx1, jx2, jxn, inverse image of that should be less than epsilon. So jxi of f minus f naught, which is f minus f naught xi, should be less than epsilon. So this defines a neighborhood. Okay, so then notation again. So we say fn converges to f, this is norm convergence. Therefore norm of fn minus f tends to 0. Then fn converges to f, this is called the usual weak convergence. What does this mean? Phi of fn converges to phi of f for every phi in V double star. And then we have fn weak star convergence, this is weak star convergence. So we have immediately the following proposition. You can do it yourself because it's exactly like we did the previous proposition. So proposition V Banach fn sequence in V star. 1. Fn weak star converges to f in V star if and only if fn x converges to f of x for every x in V. One way is obvious, the return, you just look at the pointwise neighborhood system and you will get this. So second is fn converges to f in norm. Obviously we have already seen fn converges to f weakly. That means for all functionals it converges, in particular it converges for all jx's, and therefore this implies that fn weak star converges to f. Okay. 3. Fn weak star converges to f in V star and xn converges in norm to x in V. This implies fn xn minus f of x converges to f of x. Again you take the difference and then you just have to you just take the difference and add and subtract the usual term like we did last time, and you will get it. Again, if you have it is convergent in weak star topology, it has to be bounded, because fnx converges to f of x for every x by the bounded uniform boundedness principle. Norm of fn is less than or equal to c. So we have that automatically. So we do not have anything new. Okay. So now proposition. Let phi belong to V double star. Okay, no, not V double star, sorry. Phi a linear functional on V star, which is, let phi be a linear functional which is weak star continuous. It means continuous with respect to the weak star topology. Then there exists x in V such that phi equals jx. So these are precisely the functionals which will be continuous with respect to the weak star topology. There are no other linear functionals which can be continuous. So this is okay. So let d tilde be the open unit ball in R or C, depending on what is your base field. Okay, it doesn't matter, we are going to do this. So phi is weak star continuous, implies there exists weak star open set U, neighborhood of 0 in V star, okay, because phi of 0 is 0, so it belongs to d tilde. So if you take phi inverse of d tilde, it should be an open set, it should contain a neighborhood of 0 such that phi of u is contained in d tilde. Therefore, for every f in u, we have mod phi f is strictly less than 1. Okay. Now what is u going to look like? It's a neighborhood of the origin. So this is nothing but say every f in V star such that mod f of xi is less than epsilon for all 1 less than equal to I less than equal to n. Okay. So xi in V for 1 less than equal to I less than equal to. So it's some finite collection of points you have taken, and this is a neighborhood. Okay, so assume f belongs to V star such that f of xi is 0. Then this implies that f belongs to u. Because f of xi is 0, it's strictly less than epsilon, so it belongs to u. And then also, for every k natural number, you have k of f also belongs to you, because k of xi is k times f of xi, and that also belongs to you. And this implies that phi of ku in modulus is less than 1, or mod phi of u is less than equal to less than 1 over k. And this implies that phi of f equal to 0. So if f of xi equal to 0, we have shown that phi of f equal to 0. That is, intersection of kernel jxi, I equals 1 to n, this is contained in kernel of phi. And if you remember, we have done this exercise already in the Hahn-Banach theorem chapter. This implies that phi equal to sigma alpha I jxi, which is equal to j of sigma alpha I xi, I equals 1 to n. And that's exactly what we claim. So x, the point x is sigma alpha xi, and that proves this proposition. Okay, so the only functionals which are continuous with respect to the weak star topology are the jx functionals, okay, nothing else. Okay, so corollary, a weak star closed hyperplane must be of the form H equals f in V star such that fx equal to alpha, where x belongs to V and alpha is a scalar. Okay, so we are going to prove, for simplicity, assume real Banach space. Okay, okay. So H is weak star closed hyperplane. Weak star is contained in weak, which is contained in norm, so implies norm closed hyperplane, and implies there exists a phi in V double star such that H equals set of all f in V star such that phi of f equal to alpha, because we know these are the only closed hyperplanes which in the norm topology. Okay, so alpha is some real number. Okay, so now let us assume f0 belongs to H complement, which is now open. Okay, so there exists so there exists a weak star neighborhood U such that f naught belongs to U, and that is completely contained in H complement. So what does U look like? U is going to look like set of all f in V star such that mod f minus f naught xi is less than epsilon, 1 less than equal to I less than equal to n, and xi belongs to V, 1 less than equal to I less than equal to. Okay, and epsilon is positive. Okay, so U is convex, and therefore if you remember a proposition where we studied and when doing the Hahn-Banach theorem, in fact there I remarked that everything was dependent on the ball being convex, and we would prove the same theorems of Hahn-Banach if you had locally convex spaces, namely spaces with convex neighborhoods, and that's exactly what we are having here. And therefore U is convex, therefore for every f in U, you have phi f is either less than alpha or phi f is greater than alpha. Okay, so one of these two only will happen, always only one of the, so for every f in U or for every f in U, phi f is bigger than alpha. So let us assume, so without loss of generality, phi f is less than alpha for every alpha in U, for every f in U. Okay. Now let us look at W equals set of all G in V star. This is the neighborhood of the origin. Mod Gxi is less than epsilon. So this is a weak star neighborhood of the origin. Okay. Now then what is u? U is nothing but g plus f naught g in w. Okay, so this is exactly, you put f plus f naught, then g plus f naught minus f naught is g, that is less than epsilon. So every u can be written as every element of u is nothing but g plus f naught. So you get therefore that if for every g in w you have phi of g plus phi of f naught that belongs to u, g of f plot is in u, so this is less than phi of that is less than alpha. Therefore phi of g is less than alpha minus phi of f naught. But then g is symmetric, namely g in w implies minus g is also in w, and therefore if you apply the same thing we get mod phi of g is less than alpha minus phi naught. Okay, now we can, given any epsilon or eta if you like, maybe I used epsilon somewhere, so given any eta positive we can always find f naught in H complement such that alpha minus phi of f naught is less than eta, because you can choose, because you take a point in H and then you take any point f, and then you take so H, everything is f of x, phi of f is equal to alpha, take a f naught which is phi of f naught which is strictly less than alpha, draw a line between these two, and then as you move along the line by the intermediate value theorem you can get any number which is less than eta. Okay, so this is possible, and therefore you have that there exists a weak star neighborhood w of 0 such that mod phi of g is less than eta for all g in w. This implies phi is continuous at 0, and by linearity phi is continuous everywhere. This is in the weak star topology. So phi is a continuous linear functional in the weak star topology, and by the previous proposition phi has to be equal to jfx, that is h equals set of all f such that fx equals alpha. Okay, so that proves the theorem completely. Okay. So in a finite dimensional space we already observed that all the topologies coincide, norm, weak star. In infinite dimensional spaces we saw the weak topology is strictly less than the smaller than the norm topology, and if the space is reflexive, of course the weak and weak star topologies coincide. So now if you take V non-reflexive, let phi belong to V double star but not in J of V. Okay. Then you look at the hyperplane H equals phi equal to alpha. Okay. So this is, we know, norm closed, because any closed hyperplane is precisely of this form if you take phi in V double star, and this is convex, and therefore this implies this is weakly closed. We proved it yesterday. If you have a norm closed convex set, it is automatically weakly closed, but H is not weak star closed. Okay, because it is not of the form, phi is not of the form jfx, okay, therefore it is not weak star closed. That is what we have just proved now. So if you have a non-reflexive space, the weak star, so V non-reflexive, that means automatically implies V infinite dimensional. Then you have weak star topology is strictly contained in the weak topology, which is strictly contained in the norm topology or the strong topology. Okay, so you have these things. Okay, so now you must be asking this question: what is this madness of weakening our topologies? We had a perfectly good norm topology on all our spaces, which is metric space topology, and therefore very easy to work with. Then we threw away some sets and produced a weak topology. And now we come to dual space, we throw away some more open sets and then have a, so we are impoverishing our topologies continuously, repeatedly. What is the purpose of this? If you notice, the weak open sets are pretty big. Yesterday we saw that D, bounded open set, cannot be weakly open because it contains full affine subspaces in it. So the weakly open sets are big, and so as we weaken the topologies, the open sets get bigger and are fewer in number. So this means chances of a set being compact improve. So what is compactness? Every open cover has a finite subcover. So you have fewer open sets. So already the open sets, open covers come down, and then the open sets get bigger. So hopefully a finite number of them will cover. So the chances of this, and in fact, if V is infinite dimensional, okay, and then B closed unit ball in V star is in fact weak star compact. It is compact in the weak star topology. It is not compact in the norm topology, we know. It is not compact in the weak topology either if the topologies are different, but if it is compact in the weak star topology. So you see, by impoverishing our topologies, we increase the chances of getting compact sets, and compact sets means convergence. If you have sequences, your nets and so on, you will have convergent subsequences and so on, and therefore that is important. So this is a very big landmark theorem in the weak topology chapter, which we will next